So I started to think what I'm going to talk about. And the first question that came to my mind was, what is electrical resistivity? When we measure electrical resistivity, what are we measuring, right? And believe it or not, I actually struggled with this question. So I thought that maybe I Google it. These days Google and Gemini are the same thing, apparently. So it gave me the electrical resistivity is a material property that measures how strongly material resists electrical flow. Okay, that is a definition, but it really does not give me a whole lot of understanding of what we are measuring, right? Then I opened Wikipedia, and it gave me more or less the same thing. The advantage was that it gave me some equations and units and stuff like that. But when you read it, it gives you exactly the same thing. So I had a great idea. I thought I'm going to chat with my great friend GPT. And unfortunately, ChatGPT gave me the same thing. Then I asked ChatGPT, can you draw me something that helps me to understand this better? And my question was, what is cross-optional? And there are a lot of complicated equations that I really don't understand. Then the next step was to say out of this. And really, we're going to get serious, don't we? I started to think, so what is the really fundamental things that we are measuring? If we have, we're going to start with a solution. And many of you probably already know the answer to many of these questions that I'm going to think, but these are the knowledge gaps that I have. So we said that, okay, we have a solution, and then we put two plates of metal and we provide a charge across it. We have an electric field, so the ions will move through this electric field, this electric field, and that is really shown by the so-called PMD equation, right? We don't really care about the first term, that is the diffusion. We have an electric field, the phi is basically potential, and the gradient of that is, or negative of the gradient is the electric field. And then we have a coefficient in front of that provides us, that is related to conductivity. So that provides a little bit more understanding. Okay, we are really measuring movement of ion in terms of this parameter, conductivity. And that is also related to diffusivity of an ion, which is related to mobility. Okay, these are all great. But here's the next question. What happens as these ions are moving through this pore solution? The ions will not freely move through these media. As soon as they start to move, they're going to bang into each other, right? And they're going to scatter in a whole bunch of different directions. And Vincent in 1976 actually calculated the velocity of ions under unit electric field. And he came up with these numbers. Actually, the calculations are quite simple. It's a very interesting and very nice paper to read. And if you read that, you will see that for example, chloride ion will move at the speed of around 80 nanometer per second. This is an amazingly small distance that these ions are moving, right? Of course, lighter ions will move with a higher speed. To just put this in perspective, electrons in a conductive metal will move around 100 to 0.1 nanometer per second, and that is again because you're constantly banging into other electrons or other atoms. And velocity of walking person is around half to 1 meter per second, right? It's me coming out of the bar on Friday night, it is probably 1 meter per month. but separate issue. Now, here's what things get really interesting, because what happens, we know that because of the polarization effects, that we put the electrodes in contact with concrete, the electrodes will polarize, so we have to use alternating field. And if we use alternating field, what happens? So, in alternating field, the field is constantly changing directions, so certainly the ions will not reach the limiting velocity. As soon as the field starts to switch, then, and depending on that, the distance that they move will be much smaller, and it will look something like this. This is a completely wrong animation, but that's the best thing I could come up with. The reason is that not all of them move in sync, right? Each of them move at different velocity and bang into each other, and all of them. And very interestingly, if you actually look at these Robert's data, if you measure these electrical resistivity with different devices that have different frequencies, some of them have 40 hertz and some of them a lot higher, they more or less show the same value. And the reason for that, part of the reason for that, is the fact that these ions are moving very small distances, right? Now, what happens inside the pore space? Now, this is the part that gets really, really complicated and interesting. In an alternating electric field, for example, let's say we have 40 hertz, the field direction changes 80 times, right? If you take a chloride ion that has a 79 nanometer per second, and the time is 1/80, so they're moving very small. But there are other things that are happening, because now you have the surfaces that are charged, and you have electric field from them. And again, this is this is a question that many of you might know the answer to, but this is a question that I do not know the answer. And that is how this small distance that these ions move correlates to the long distances that we are interested in diffusion tests, right, under concentration gradient. And another question that I got interested in answering was, if ions are moving such a small distance at the order of a few nanometers, why would the structure of the solid actually matter? Right? And it would matter due to few reasons, especially in terms of cement paste. Of course, we are dealing with a very small and complicated geometry of the structure. That's a lower cast road, bottom of cast road, and x-axis shows the Kelvin radius. And you can see that the radius is very small. And the electric field, or the surface conductivity, the surface charges that we have are also playing a role. Now, I'm not going to go into a lot of these details, but of course, the formation factor was introduced in 1942 by Archie, and this was the equation that was used. And Hans Olaf, I will let you read the last name, I'm not going to pronounce it. He actually tried to relate that to the pore space and pore surface area. It turns out that relating it in terms of theoretical calculation turns to be very complicated. And it's a lot easier to think about this parameter as a lumping parameter, something that you measure, and it basically accounts for all of the microstructural effects. Right? Direct theoretical calculation of that would be very challenging. Finally, again, I think I know that there are a lot of good experimental data in terms of relating resistivity or resistivity measurements of formation factor to actual diffusion. The things that I'm really interested in, and hopefully some of you know the answer of that and you can share it with me, is that how does small distance movement of ion actually relate to large distances that ions need to move during the under concentration gradient. Finally, I just wanted to share an artwork by ChatGPT which showed me how resistivity measurements of concrete should be done. Thank you.